now we see that in a particular part program, actually part programs are nothing but they are actually particular form in which the with which the manufacturing people have been familiar and convenient, but otherwise it just like it just specifies some operation. So, every unit of operation is called a block, right. So, part program block. So, the part program basically consists of a number of blocks which get executed. So, in a sense it is like it is like these PLC rungs. So, if just like a real ladder logic diagram is also just a fictitious graphical arrangement, so that people who develop programs, that is the people from the domain, they can understand it. So, similarly here we write part programs. So, then finally these part programs are going to be from the part program the actual real time executive which controls the two drives, this it reads the part program and then actually drives the various activities in the machine. So, the first, so you can have such parameters in a typical program block, like you can have a block skip, you can have a block skip. So, if you have that block skip, then that particular block is ignored. Similarly, you are executing a sequence of blocks, so you should have a block number. Then there are some functions which are called preparatory functions. For example, deciding on whether the positioning system is going to be absolute or incremental, whether the values which are given are in metric or in inch, where is the origin of the coordinate system, etc., etc. So, there are some preparatory functions that are to be executed before executing a block. Similarly, dimensional information is provided as in XYZ. Okay, decimal point is fine. Then you have to provide things like feed rate, spindle speed, tool number, because tools are uniquely identified by their number in a magazine. So, if the machine has to select a particular tool, the tool number has to be given. Similarly, the tool offset functions. So, there are actually what happens is that for exact dimensional accuracy, there are, because the tool has a finite radius, the tool actually has a finite radius. So, when the tool moves, because of this, there is some distance between the center of the between some logical center of the tool tip and the actual point where it is making a contact, and it's not only making a contact, it's actually gradually getting worn away. So, this length is actually changing, it's actually shrinking. So, there are various kinds of offsets are produced, and these that is when you are actually giving the motion. So, you have to give the motion to the tool in such a manner that after taking care of this finite tool head situation, then the right parameter will be obtained. So, therefore, the tools must be a little bit offset. So, those functions are to be set during preparatory phase, and there can be various other miscellaneous functions. There can be other various kinds of auxiliary functions also, like switch off coolant, switch on coolant, and things like that. And finally, it has to have an end of block signal. So, typically you see a block is defined like this. This is the number, then there is a G command, then there are some XY commands which are position coordinates. Even apart from that, there are various other kinds of commands which are specified. So, we are not going to look at all of them. So, in short, a particular program block will actually contain such a set of instructions. Sometimes these instructions are mostly optional. So therefore, you may or may not have some instructions. There can be only one so called operand, and there can be, or there can be even 6-7 operands in a particular instruction depending on the requirement. So when you CNC machines are typically characterized or classified by a number of features. So some of them are being mentioned here. So you have number of controlled axes, so 2 or 4, and so the same machine may have a number of controlled axes. What kind of interpolation you are doing, whether it's linear or whether it's circular or whether it can be parabolic, etc. Then what kind of feedback you are using, whether you are using digital feedback or you are using analog feedback, what is the basic length unit. Similarly, the feed rates, maximum feed rates that can be achieved, and there are certain per minute or per revolution, and there are certain other modes related which are called rapid traverse rates. So when you are moving from one hole to another, so you have drilled this hole, when you are moving to another, then during this time you are not actually cutting, and you need to move at the fastest possible rate. So that is called a rapid traverse rate. Then the kinds of the part programs that can be that are used to program it, this is maximum size, IO devices, etc., various program parameters. Also some programming parameters, that is, if the operator or some engineer wants to develop a new program, then how easy it is, and I mean how it is to be loaded. So there can be various methods, for example only manual, or can be background, foreground. So when you have background, then you are actually doing things normally, but you can always go to what is known as the background and then start developing some program, while in the foreground something else like a manufacturing operation is actually going on. Similarly, the various environments in which the program developer has to work, that can be graphical or that can be menu driven. These are very standard things today. So one has to examine what kind of programming facilities exist in the machine before buying it. Similarly, since accuracy is generally a very major issue, so therefore one has to really look at the various kinds of compensations facilities that are available in the machine, because they are typically used for achieving a very high accuracy. So for example, there can be backlash in the gear, or even there can be backlash in the shaft angle encoder. So it can be either on the gear or in the ball screw. It can also be on the shaft angle encoder. So there can be lead screw pitch error, that is, one rotation of the lead screw may not lead to an advancement of exactly the same amount all along the screw. Then there are compensations required for tool length and the cutter radius, the thing that I was just talking now. Because of the finite dimension of the tool, you need to create such a motion such that the tip actually cuts according to the position where you want to cut it. But for that, the tool has to be moved in a certain with certain offsets. So these offsets are to be always because the tool will get worn. So therefore these offsets are to be regularly measured, and then the proper compensation should be given. Similarly, temperature, for very high temperature, firstly product quality can be affected, and secondly sometimes dimensions can also be affected. Various kinds of thread cutting that are possible, and then what kind of PLCs are used, how the PLC is going to interact with the drives controller, and the number of IOs that it can handle. You see that typically, as we will see, that the PLC is not to be used for the drive, for the drive so close sampled and control is required, and sometimes the computation is also involved. So, under these situations it will not be really useful to so right. So it will not be really useful to actually use a PLC to provide a control of these drives. So, therefore, some special dedicated processors are used, and the PLCs are often used for auxiliary functions or as supervisory controllers. So, we look at architectures of CNC machines. So, that is what I was saying, that typically a CNC machine will be made of this kind of units. So, you have the basic mechanism, that is the consisting of the slide, the screw, the gears, the guide, the chuck, etc. So, these are the mechanisms which hold, and actually mechanical parts which hold and move the job and the tool. So, they are driven by motors, typically servo motors. This can be DC, BLDC, or even induction motors sometime. So, these motors are, as we will see in our future lessons, that these motors are to be driven by very sophisticated drive. So, these are power electronic devices, plus they are controllers, control electronics. And now these are again controlled by these. So, these control electronics and the power electronics is often controlled by microprocessor based. Sometimes in this case their modern machines are becoming DSP based or digital signal processor based drives, which can provide very sophisticated control for these machines. Along with that, we also have another kind of computer called PLCs, that is what we are saying, which is mainly used for discrete automation. And there is also a man machine interface which lets the operator program it and also monitor the status of the machine, and also there are mechanisms for generating various kinds of alarms. Okay, so this is the general structure of a CNC machine. Typically, the drives that are used are sometimes they are open loop, especially when they have switched let's say low power drives like stepper motor drives, which are cheap because they are actually their drive electronics is much simpler. So, we have these sometimes we have used this kind of drives which are open loop and use very simple drive electronics. So, we can have, in the case of motors, we can have step motor drives, or in the case of hydraulic drives we have proportional valves, where we just give a command and a proportional force or displacement is. So, you can have a hydraulic motor or a step motor, and so the machine is driven in open loop. But the best and the most accurate drives are all naturally that they are closed loop drives. So, you have the usual motor, so which can be AC or DC, or sometimes we have what we known as a brushless DC, which is actually an AC motor, but which behaves like a DC motor. So, it has the advantages of both the worlds, or it can be a hydraulic motor also. And then we have the servo drive for the hydraulics, which is again controlled by the various kinds of digital and analog electronics, digital processors and analog electronics. and finally we have the sensors which give the feedback. So, these are the closed loop drive configurations which are typically implemented for these machines. So, now we will take a look at the drive requirements for these machines. So, we have two kinds of drives. One drive is a feed drive. So, if you see, basically if you see the load on the drive, then the load is given by an expression like this, where the load torque, this is TL, load torque, is the torque. So, this is the force, this is the cutting force which is occurring at the which is in this case, let us say in the case of turning, which is occurring at the tip. In the case of turning, the feed drive is moving the tool, right. So, the job is rotating, like this, and the tool is moving, job is rotating at one position and the tool is moving from one side to another, right. So, the force is being created on the tip of the tool and the tool is being driven from a screw. So, the screw is rotating here, so the tool is moving. So, the load on the screw, which can be reflected as a load on the motor through the gearing mechanism that is used, is can be calculated by this force multiplied by this length arm, lead of the ball screw, also cutting force required in axial direction of feed. So, then that is the lead of the ball screw, and then so how is this achieved? Because if you have, it is achieved by something like energy conservation. So, the torque into one rotation of the screw is going to be the force into the pitch, because if by one rotation of the screw the linear motion created is one pitch unit. So, therefore, if we have energy conservation, then F into the pitch of the lead, the pitch of the ball screw must be equal to the torque, because one rotation. So, one per rotation is twice pi radians. So, twice pi into TL, this is the input energy. What is the output energy? The output energy is this force into pitch and multiplied by some efficiency factor. So, input and output factors will have efficiency, plus there are certain other friction torques. So, this is the load torque, and we see that it remains more or less constant, right. So, it remains more or less constant irrespective of the speed. So, irrespective of the speed, it remains constant. Similarly, so you see, just to explain that, so this is the ball screw. So, you have weight on the slide and you have various friction forces, number one. Number two, you have cutting force. So, all these forces are going to be reflected as load torque on the screw through this mechanism. So, these are the spurious load torques. So, because of the weight, you have friction, you have bearing reaction, and this is the main force, which is the cutting force. So, Tc is friction torque and eta is efficiency. So, F depends on the machine design and the material removal rate. So, the depth of cut. So, you see that the torque actually depends on the, in a way it depends on the material removal rate. So, it depends on the depth of cut as well as the feed. So, if they are generally constant, then a constant torque operation is needed on the feed drive, correct. Sometimes it may happen that for short times, because of material inhomogeneity that is encountered, sometimes these torques can suddenly rise to a very high values, but that should not affect the cutting. So, therefore, the for short periods the machine actually should be able to handle, the machine actually should be able to handle good amount of overload torque. So, high overload torques for short durations, such drives should be able to provide, while for continuous duty at much lower level of torque may be uh, achieved. For the spindle, it turns out that again the drive requirement is related to the quantity of material removed. So, the quantity of material removed is feet per revolution of spindle, okay, feet per revolution of spindle. T is the depth of cut and d is the diameter of the workpiece of the cutter and eta is the RPM. Then linear velocity is naturally pi d eta by 1000. So, so this is the linear velocity. So, this linear velocity into S into T, this gives the quantity of material removed. Okay. Now, the power, it turns out that for the spindles the power is actually proportional to Q into Ks, where Ks is actually the what is known as the specific cutting force per unit chip cross section. So, it depends on the material and it depends on both the material and the workpiece, and Q is the material removal rate. So, in this case it turns out that the power depends on the material removal rate. So, therefore, for constant material removal rate, typically in manufacturing we are going to fix that, we are going to fix the material removal rate depending on the kind of production that we want to have. So, for the spindle drives we have constant power requirement generally. So, the spindle drive characteristic is generally of this shape, where you have a large constant power region, and so this gives the maximum speed. So, irrespective of the speed, a constant power is to be kept. So, we will see later when we see the various drive characteristics, that how in the motors we actually have these regions of constant torque and constant power. So, we will operate these drives accordingly in the various regions. So, in the desirable features of machine drives are, spindle drive should be accurate from the rotational speed point of view, while feed drive should be very accurate in terms of position resolution, in terms of microns. Spindle drive should have fast dynamic response and very wide. On the other hand, feed drives could be operated in very wide speed ranges. So, for some materials they could move real fast, for some materials they can move real slow, especially that also depends on the on other things like surface finish. Similarly, overload capacity, 4 quadrant operation, for example, feed drives, because they need very good positional accuracy, they always have to have 4 quadrant operation, while spindle drives generally do not require that. They have unidirectional motion, they can be 2 quadrant motion is enough, and very high speed braking etc. are not needed at all. But there can be large overloads encountered, especially due to material homogeneity. So, while the speed range should be large, but it need not be excessively large. Similarly, so feed drives require a very good transient response. So, they require very fast response. So, low electrical and mechanical time constants are needed, and they need constant working torque. Spindle drives on the other hand should be of much more compact size, because they are generally to be mounted on a spindle which should not take too much, should not be too big. So, we have come to the end of the lesson summary. So, we have come to the lesson summary, and so what have we seen? So, we have seen the basic structural features of a CNC machine, what is made it, you have seen its basic operational features, how it works, and we have seen that basic structure of programs. So, we have seen basic look into the blocks, and we have looked at the drive requirements, typical drive requirements for spindle and feed drives. We have also seen the basic advantages of this machine, that they are much more accurate and much more flexible. So, among some points to ponder, you can name the main components of a CNC machine. So, try to name them, mention its major advantages and the main reasons, that is main technological reasons from which these advantages arise. Name 3 features of a part program block, so various features. Mention 3 differences in the requirements of a spindle drive from that of a feed drive, how they are different. So, that is all for today. Thank you very much.